us to do is graph 4 minus x squared. So what is that? If we picture what that's going to look like, it's x squared, so that means it's a parabola reflected over the x-axis. What's that 4 going to do? Up 4. So we're going to need to go on the x-axis here. We're going to need to go up 1, 2, 3, 4. And then we need to have 2 over here on the y-axis. 4 minus 0 squared is going to be 4. So when we plug in 0, we get 4. If we plug in 1, 4 minus 1 squared would give us 3. So 1, 3 would be right here. And then 4 minus 2 squared is going to be 0 right here. So we're looking at this piece of the parabola. Okay, so, and it tells us that we're bounded by the x and y axes. So if I kind of highlight our boundaries here and look at the area we're trying to look at, you know, we got the x and the y axis are our boundaries, and then we've got the function itself as a boundary. So the highlighter sometimes doesn't want to let me highlight what I want. Straightens it out. But we're looking at this area right here underneath the curve. So this first problem says to use rectangles under the curve to estimate. And for this first one, I'm going to use, I think I'll use 4 rectangles. Okay, so it is going to be easier on this if I split this into even increments. So right here is 2, and I'm just telling you that I want you to use 4 rectangles. So I need to split this into equal pieces right here. So I would have this. Now, if I want to draw a rectangle underneath the curve here, so let me use the rectangle tool here so I have a nice pretty graph. I would make a rectangle and I would go up until it touches the graph right there. And then I'd go to the next spot here, and I'd go up here until this touches the graph. Same thing here. Now here's the thing on the last one. Can I really even do a rectangle here? I cannot. I could make a triangle, but I'm saying we have to use, I'm kind of doing like I did with toilet paper squares. We can only use rectangles, and there's going to be a reason for that. Because what we're wanting to do is we're wanting to make this systematic, not just do the best you can, guess at it, right? We got close-ish, some of us did, just guessing at it. We want to make this systematic. It's going to make our estimates worse at first, but it's going to lead us to a path where we can find the exact value. So, although this is really only 3 rectangles, it's 4 intervals that we're looking at. So we would consider this to be our 4 rectangles here, even though that last one does not have a rectangle because it couldn't have any height right there. We don't want to go above the graph. So if I want to find the area of each of these rectangles, what would the width of each rectangle be? 0.5, right? So we got 0.5 right here. We got, oh gracious, I know I shouldn't use the stupid rectangle. It goes crazy sometimes. I'm not even trying to use a rectangle. Okay, let's go back to the pen. Alright, so we got 0.5, 0.5, 0.5, and if we want to use this last one, 0.5, right? What would the height of this first one be? Yeah, it's not 4, because 4 would go all the way up here. 3.8-ish. Again, we don't really want to guess on this, right? We can figure out exactly what this is, because this corner of that rectangle should be on the graph. How do I find how high this point right here is? we plug in 0.5 into the equation, right? So if I do 4 minus, I'm going to use 1/2 instead of 0.5. Well, yeah, I'm going to use 1/2 instead of 0.5. You can use 0.5 if you want, I guess. So we got 4 minus, that'll be 1/4 whenever we square it. And so that'll be 4 minus 1/4, which is 0.25. It's going to give us 3.75 there. So this rectangle has a height of 3.75. So I've got 0.5 times 3.75 for that rectangle 1. All right, and we're going to use our calculator some on this. These usually end up being non-calculator problems for these, but our textbook's not really written like that. So if you're just using your calculator for basic multiplication, addition sort of stuff, you may do that. So we get 1.875. We also could do fractions, so we wouldn't even need the calculator, or you could do it by hand. All right, so this first one is 1.875. What is the height of the second rectangle? It is 3. And if I plugged in 1, it is exactly 3, right? Because if I plug in 1, 4 minus 1 squared is going to give me 3. So I'm doing, for that second rectangle, I'm doing 0.5 times 3, which is going to give me 1.5. So that's the area of that second rectangle. And then if I do the next one, I do not know the height of this one. I can't tell it from the graph. What do I need to do to find the height of that rectangle? 1.5. So if I do 4, do it over here, 4 minus 3/2 squared, I'm going to get 4 minus 9/4, which is 4 minus 2.25. So I'd get 1.75 for that. So if I do 0.5 times 1.75 here, I'm going to get 0.875. And for this last one, I really don't have a rectangle, but just for the sake of consistency, that last rectangle, it'd be 0.5 times a height of 0, right? Because like that right-hand edge of the Riemann sum would be on the x-axis there, and so I'd get 0 for that. So, okay. All right, so if I add all of those together, 1.875 plus 1.5 plus 0.875 plus the 0, if you want to put it on there, is going to be 4.25 units squared for this. Okay, questions so far? Does this seem very accurate? We got a lot of gaps right there, right? Is this an overestimate or an underestimate? Definitely an underestimate, right? Underestimate by quite a bit. If you need to be precise, this would not be good enough here. But what we're working on here is like a systematic way to do these problems. So let's go to the next part. I want to do the same thing. I need to fix my notes here. I want to, this time, use rectangles over the curve. So, same graph. 1, 2, 1, 2, 3, 4. We've got, yeah, we're just graphing the same thing again. Here. And we're looking for that same area that we found on this last problem, we are still going to use 4 subintervals. So let's split this x-axis into 4 sections. But this time we want to use the rectangles that are above the curve. So I'm going to use that rectangle again so I can draw this neatly. Alright, so the rectangle above the curve is going to look like this. Okay, its highest point is going to be at the top of the rectangle. And then I would have this. And this. And this. Now, are we going to get an overestimate or an underestimate with this one? Over by quite a bit once again, right? Neither one of these alone is going to be all that great. But we still can figure something out for this. So once again, we've got 0.5 is the width of each one of these rectangles, right? What is the height of the first rectangle? It is 4. So we're going to have 0.5 times 4. And that will give us 2. So the area of that first rectangle is 2. What's the height of the second rectangle? It is 3.75, because this is that same point that we used on the first rectangle there, right? If we plug in 0.5, we will get 3.75. This is the point. 0.5, 3.75 are the coordinates of this point right here. So we're going to have 0.5 times 3.75. And that is going to give us that 1.875 that we got earlier. So that's the area of this. All right. What's the height of the third rectangle? It is 3. Because, again, if we plugged in 1, which would be the coordinate of this point right here, we'll get 3. So we'll have 0.5 times 3. That will give us 1.5. So the area of this rectangle is 1.5. And then our last one, this time we do have a height of that last rectangle. What would the height of that be? Looks like about 2 on my graph. We need to plug it in to see for sure, which we did do on the last problem, right? If we plug in 1.5, or 3/2, we got, what was it, 1.75, I believe, for that. So we'll get 1.75 for the height, and that gave us 0.875 for that. So if we add all of those together, we are going to get 6.25. Now, we know for sure that would be an overestimate because all those rectangles are above the graph for this. So, all right, next slide. How could we make our estimates better? Okay, so one option, we could average the over and under estimates. And we know that would give us an idea. It's not going to be the, except for certain functions, it's not going to be the exact value. It's going to be a lot closer than our original estimates, right? So that's an option. What else? What else could we have done over here. More rectangles?
Different shapes.
Okay, let's start with the more rectangles idea, and then let's talk about the different shapes idea, because those are both good ideas. Because if we have more rectangles, think about looking at this. If I do lots of teeny tiny rectangles under the curve, teeny tiny ones, the graph's not great, but do I have as much open space if I do those teeny tiny rectangles? All those little gaps are a little smaller, right? So like if I did 8 rectangles instead of 4, my estimate would be better. If I did 16 rectangles instead of 4, it'd be even better, right? What would be the best? What? A million? Million would be good. What would be better than a million? Infinite, right? So that's that idea where we're going with this. Limit as x approaches infinity is going to come into play here. Because if we had infinite rectangles, then we could know the exact area, right? Now, we couldn't figure out, like a million, if we had to do this a million times, if we took 2 and divided it by a million, and each, like if I made you guys do that, it would take us till the end of time to figure out a million, right? So infinite is not possible to do. A million's really not even possible for us to do. It technically maybe is possible, but not in any useful sense, right? So we're working towards this idea where we can get this to be exact with lots and lots and lots of rectangles. Smith had a different idea. Instead of more rectangles, he said different shapes, right? What would work better, Smith, than rectangles?
I feel like rectangles were pretty good in that one. I guess triangles sometimes.
Yeah, and like we did this sort of whenever we didn't do that when we were doing our toilet paper because I told you couldn't cut your toilet paper, right? I told you had to use just whole pieces of toilet paper. But whenever we did this on the first set of notes, we would like, instead of using a rectangle, we'd cut this off right here and make it like a little triangle on top of a rectangle, right? Or it technically is a trapezoid there. So we could use different shapes. Particularly helpful are going to be trapezoids, but we could use other shapes as well. And that would give us a better estimate for that. So these are all good ideas that can give us better estimates than what we got to begin with, because there's probably not much that we would be doing where these estimates would be close enough, right? I guess if you were like, I don't even know what, let's say you're pouring concrete for this area right here. I guess at least if you get that 6.25, you know you need at least that, you need probably, you could order that much concrete and then you'd have some left over. You wouldn't want to go with the underestimate if you're doing pouring concrete. You'll run out, right? So, let's continue. Now today we are just working on left and right Riemann sums, all right? So we are just doing these kind of bad rectangle estimates, right? Because we're going to have to learn how to do these estimates. Then we'll learn some estimates that are a little bit better than these not great ones that we're doing. And then we're going to work towards the end of the week looking at what happens if we have infinite rectangles. What would the exact value be? So that's what we're working towards. But first we got to learn how to do some kind of like bad estimates here, right? We're supposed to estimate the area between the curve of y equals x minus 1 to the third power plus 2 and the x-axis on the interval from 0 to 3 using 6 subintervals. Okay? And they want us to do a right endpoint Riemann sum and a left endpoint Riemann sum. Okay. So the first thing we want to do for a problem like this is we want to make ourselves a graph. This one's a little harder to get a graph for, and this is where it kind of helps to have a picture of what's happening. You got a cubic function. What's this minus 1 right here do to that cubic function? Right 1. What's that plus 2 do? Up 2. Our other restrictions are it has to be the x-axis is a restriction. Since we got that cubic moved up, it's above the x-axis, right? And we're looking on the interval from 0 to 3. So I know my x-axis is just 0 to 3. I know I want first quadrant here. If I plug in 0 into this, actually, really, I care about 3. If I plug 3 into this, what will I get? I get 10, right? 3 minus 1 is 2. 2 to the third is 8. 8 plus 2 is 10. So I know my graph needs to go up to at least 10. You want to think about these things before you start graphing these by hand, because if you don't, then you're going to end up running out of room. So if we graph this, we do a graph here. I need this to go 1, 2, 2, 3, and then we need to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Right here. So definitely we want to at least get a few points so we can get a relatively close graph. If I plug in 0 right here, I'm going to get 0 minus 1 is negative 1. Negative 1 to the third is negative 1. Negative 1 plus 2 is 1. So you'll get 1 if you plug in 0. In fact, let's make ourselves a table because it actually might be helpful for us. 0, I'll get 1. I bet I have 6 subintervals. How wide is each interval going to be? If I'm going from 0 to 3. I need to cut it into 6 intervals. 0.5, right? So I'm going to have 0.5, 1, 1.5, 2, 2.5, and 3. For our graph, let's just do the whole numbers right now. 1 minus 1 is 0. This will give us 2 right here. So we got the 0.12. If I plug in 2, I'm just going to get 3. 2, 3. And if I plug in 3, we already said we get 10. So that graph really shoots up over here on the end. And if you remember sort of the shape of a cubic function, right here is what we're looking at for this. So, whenever we do this, we have right endpoint Riemann sums and left endpoint Riemann sums. Okay, a right endpoint Riemann sum, if I split this into 6 subintervals like it asked me to, that means each little rectangle is going to have a width of 0.5. And it means that when I draw this rectangle with a width of 0.5, I want the right corner of that rectangle to be on my graph. Okay, so this would be a right Riemann sum. So right here, I would want the right corner to be on my graph. Right here, the right corner on the graph. Right here, right corner. And right corner for all those. So whenever I'm doing this problem, I'm going to find the width and height of each one of these rectangles, I'm going to add all of those together. Is this going to be an overestimate or an underestimate? Over. So, for this first rectangle, what is the height of that rectangle, or what would I need to do to find the height of the rectangle? Because that corner right there that is on the graph, its x coordinate is 0.5, right? So we're going to plug in 0.5, and for the sake of time on this, we are just going to use the calculator. So let me pull this up. Where's my, there we go. Alright, so for this, we actually could even do this to save ourselves a little bit of time. We could do x minus 1 to the third plus 2 and put that into y equals. We could go back to the main screen and we can just do y1 of 0.5. And that's going to give us 1.875. So we get 1.875. So that first, oh gracious. I don't know why it's doing that. Will it go away? There we go. Okay. So that first rectangle would be 0.5 times 1.875. Which is going to give us 0.9375. Okay. All right, what's the height of the next rectangle? Two. We would plug in 1 to get this, right? Because that point right there is at 1, and the value that we get when we plug in 1 is 2. So we would do 0.5 times 2, which will just give us 1. That's our second rectangle. Our next rectangle, what number do we need to plug in here to get that height? For that. If we're looking for that third rectangle, this point right here is the highest point on that rectangle that's on our graph, right? What's the x coordinate for that there? 1.5. So if we do y1 of 1.5, we will get 2.215. And then we have to do, I'm sorry, 125. Write that down wrong. And that is going to be 1.0625 for that. Let's do the crazy thing again. Okay. All right. Okay. What do we get for the next rectangle? What's that height? That is going to be 3, because if we plug in 2, it is going to give us our value here. That's going to give us 1.5. Then, for the next one, we need the height of that fifth rectangle. What number would I plug in to find that? 2.5. So if I do y1 of 2.5, that is going to give me 5.375. 5.375. 5.375. And that is going to be we take half of it. We get 2.6875. And our last rectangle, what's the height of that last rectangle? 10. Okay, and half of 10, of course, is 5. So then we have to add all of these up. 375 plus 1 plus 1.0625 plus 1.5 plus 2.6875 plus 5. And we will get 12.1875. That seems like so much work for a bad estimate, doesn't it? And that's even using the calculator. If you had to do it by hand, it'd be even worse, right? So let's talk about some things that we might could do that would make it faster to figure this out. We're still doing the estimate. We're not getting the exact value, but just would make it faster for this. Essentially, what I was doing was 0.5 times 1.875, 0.5 times 2, 0.5 times this. I did 0.5 times everything, and then I added them all together, right? Since I am multiplying everything by 0.5, right, could I do this? Would it be okay to pull the 0.5 out front there, since you've got a 0.5 with everything? Okay? So, like, if I had 0.5 times 1.875 plus 2 plus 2.125 plus 3 plus 5.375 plus 5, that would help me a little bit, right? At least I don't have to do all these middle calculations. Oh, yes, it would be. Thank you. I was using the wrong number there. Did I get the rest of them? Yeah, the rest of them are okay. So if I type that in, I would get 12.1875. That would be a little teensy bit faster. Not a big deal, but a little bit faster, right? Let's talk about what each one of these things right here are. Okay? If I think of this as like, let's call this f of x instead of y. 1.875 is what you get when you plug in what value? 0.5, right? So this is f of 0.5, right? And this is f of 1. And this is f of 1.5. And this is f of 2. This one's f of 2.5. This one is f of 3. So if I'm letting you use your calculator for this, right, and I'm going to on these for this, then I could do 0.5 times, I could do y1 of 0.5 plus y1 of 1 plus y1 of 1.5 plus y1 of 2 plus y1 of 2.5 plus y1 of 3. And that would give me the answer right off. All right. So, since I'm letting you use your calculator, rather than having to do all of these calculations by hand at once, if we just typed in our equation and typed in this right here, it would give us the answer right off. Let's try that doing a left endpoint sum for this one, okay? So I'm still going to graph here for the left endpoint sum. If you don't have room, I know it may not have a lot of room, but I did at least print these bigger. I'm going to draw the graph again. So just the same graph from above. And we're just going to graph those same points that we graphed before. Like this. And we are, once again, splitting this into 6 subintervals. But this time it's asking us to do a left endpoint Riemann sum. Right? So a left endpoint Riemann sum means that the left corner of your graph, of your rectangle, has to be on your graph. All right? So for this one, it would look like this. Right here. This is going to be an overestimate or an underestimate. Under by quite a bit, right? It's not a great estimate, but it's under. Okay, what is the width of every interval here? 0.5, right? So instead of doing what we did last time, where we found out each individual rectangle, let's put our 0.5 out front. Right, that's our width. And I'm trying to avoid having to type all of this into the calculator. I could, like I did on the last problem, but I'm trying to make it a little bit faster. So, this first rectangle, what's the height of the first rectangle? It is 1. But if I want to use my calculator for the whole thing, I could put a 1, definitely, because I can see that here, right? But let's say that I'm not really wanting to have to figure all that out. I could call it, instead of calling it 1, I could say f of, what's my x value there? It is 0, because we're talking about this left corner this time, so it's going to be 0. So I'll have f of 0. What will be the next height? It's going to be 0.5, right? So I'll have f of 0.5, and then this is just going to continue, right? I'll have f of 1, f of 1.5, f of 2, f of 2.5. Do I use f of 3? I do not. So if you kind of look at what I typed in up here, for the right-hand Riemann sum, I did not use 0, right? I didn't use f of 0. I used the other 6. For the left Riemann sum, I did use 0. I did not use 3, right? Because what we have here, if you look at this table from 0 to 3, you've got 7 points. But you only have 6 rectangles. So if you're doing the right endpoint Riemann sum, you don't use the first one. You do use the last one because it's furthest on the right. If you're doing a left Riemann sum, you do use the first point. You do not use the last one for this. So since I already have this typed in, all I've got to do is go over here and take off this y1 of 3. And, I mean, you don't even have to put this at the front if you don't want to. You could put it at the end, and add in the y1 of 0 right here, and it is going to give me my estimate. So I'll get 7.6875 for that. So 7.6875. That one is definitely an underestimate. The first one was overestimate. So we know our answer should lie somewhere in between there, right? Okay. Now, I do want to talk about one more little quick thing real quick before you guys have time to work on your assignment here. This was a right endpoint Riemann sum. Right endpoint was an overestimate. Left endpoint was an underestimate. However, if we go back to this graph right here, was this one a left or right point. That one was a right. This was a right endpoint. And it was a underestimate. Okay, and then this one was our left endpoint. And it was an overestimate. So definitely left endpoint and right endpoint don't necessarily give us our overestimate or underestimate. How can we tell if the left endpoint is going to be an overestimate or an underestimate? Okay. If the slope is positive or negative, I also heard Jeremy mention something over here. What'd you say? With concavity? All right, let's explore this a little bit. I'm just going to look here. So basically we got 4 options, right? We could be increasing concave up. Okay, so increasing and concave up would look like this. Okay, let's consider the left endpoint. All right, left endpoint. If I do left endpoint here, where my left endpoint of my rectangles is on the graph. Left, is that going to be under or over? Under. Okay. Let's consider increasing concave down. Okay, increasing concave down would look like this. Okay, if I do left endpoint, so the left corner of that rectangle's on the graph, over or under? Still under. Right? Let's consider our decreasing graphs. It's looking like maybe concavity doesn't matter for this. Let's see our decreasing graphs to see. Decreasing concave up. So if we have a graph that is decreasing but concave up, so that would look like this. Let's think about that left again. So decreasing. Draw my line so it goes on out. Left. This time would look like that. That's over. And if I have decreasing concave down, so decreasing and concave down would look like this. If I do a left endpoint here, also an overestimate. So, concavity actually ends up not mattering on this, whether or not you'll get an overestimate or an underestimate. So, if you have a function that is increasing, your left Riemann sum is going to be an underestimate. Your right Riemann sum would be an overestimate. If the function is decreasing, left is an overestimate, right is an underestimate. If the function both increases and decreases, then you don't know if you have an overestimate or underestimate, because part of it would be an overestimate, part of it would be an underestimate. It would be a lot like some of our graphs we have up here. We can't really tell whether it's over or under. Like this is a great example right here. It's over in some places, it's under in some places, so it's hard to tell which one it's going to be for that. Okay, questions? Okay, so you were just practicing with